Dear friends and followers, welcome back to my channel, and in this video we're going to see how to design and simulate a microstrip line in Advanced Design System. So let's get started. So the first thing is to know what parameters we know about this design and what parameters we have to find. So the first thing is to know the type of the transmission line we're going to design. In this video, we're going to go over the microstrip line, but we have different types of lines, such as coplanar waveguide with the ground planing underneath, strip line, or any other types of transmission line we have. The next step is to find the material that we're going to use for this implementation. For example, we have FR4 material, Rogers material, or any other type of material available in the market. Next step is to find a good board thickness. Are we going to use the standard 31 or 62 mils, or we're going to make it like a custom-made design and select the thickness according to our design, like 20 mils or 5 mils. The other step is to find a correct conductor for this design. As you know, we have different types of conductors. For example, we can use copper, aluminum, gold, or any other type of conductor. After finding these parameters, then the unknown is the line width and the line length in order to get a correct characteristic impedance, for example, standard 50 ohm, and the line length based on the amount of phase shift that we want to have in this implementation. So after finding these parameters, we have to have an estimation of the design. For example, here is the implementation of the line. You can see that the width of the line is an unknown in this case. We're going to use an FR4 as the substrate, the PCB material. The PCB thickness is 31 mils. I'm going to use the standard thickness, which corresponds to 787 micrometer. The PCB material parameters are shown here. The epsilon R is 4.4. The dissipation factor is 0.017 at the frequency of 2.4 gigahertz. The other important parameter that we need to know is the thickness of this metallization. I chose 1 ounce copper, which corresponds to 31 micrometer. This is again standard value for this implementation. And pay attention that the thickness of the thickness of the ground plane at the bottom is exactly equal to the thickness of the line top. And the conductivity of copper is 5.96 times 10 to the 7 Siemens per meter. Okay, after knowing all these parameters, the next step is to add these values in ADS line calculator and find the width. Okay, so let's do it. Alright, so I'm going to go to the tools, line calc, first option. I'm going to select that, so it opens another window for me. In the top left corner, we can select the type of the line. This is like microstrip line, but we have different options. For example, we can use coplanar waveguide, grounded, or any other type of line that we want. Okay, so we're going to keep it as a microstrip line. So I'm going to add all these values that we have for the FR4 material and also the metallization. So the epsilon R is 4.4. I'm going to add it here. Mu R is not important in this case. H is the thickness of the PCB, which was 31 mils, or if you want to use the value in the micrometer, it was 787 micrometer. HU is not important. T is the thickness of the line, so it was like 35 micrometer. Conductivity. The conductivity of copper was 5.96 times 10 to the 7. Dissipation factor 0.017. The frequency 2.4 gigahertz. The characteristic impedance that we're looking for is 50 ohms, and the phase shift of this line is 90 degrees. I'm going to change these units into millimeter, I'm sorry, so I give all the values here. Let me check micrometer, micrometer, and gives me these values in a millimeter. Okay, so now if I click on synthesis, it calculates all these values for me. So the width of the line is 1.47 millimeter, and the length of the line is like 17.26 millimeter in order to get 90 degrees of phase shift in the line, or basically a quarter wavelength line at this frequency. Okay, so now we are ready to run a simulation to see if these values are right. And in order to do that, I'm going to go in the schematic window. I'm going to go to the Microstrip palette right here, transmission line Microstrip. I'm going to put the substrate material here first, and I'm going to add the previous materials here real quick. So the H was 787 micrometer, epsilon R 4.4, mu R is not important, conductivity 5.96 times 10 to the 7. T is the thickness of the copper, which was 35 micrometer, dissipation factor 0.017, and the other parameters are not important in this simulation. Okay, so I'm going to hit OK, and then I'm going to click on the Microstrip line, and as you can see here, you can change the width and the length of that transmission line. And please make sure that the substrate material of this line is pointing to the substrate parameters that we already have in this design. Okay, so based on the line calculator, the width of the line should be 1.47. I'm going to add it here, 1.47, and please make sure that you change the unit into millimeter. And the length of the transmission line was 17.26 millimeter. Alright, so I'm going to use this parameter simulator here. So around 2.4 gigahertz, I'm going to add 2 gigahertz of span around it, 0.01. I think that accuracy is high enough. Okay, so I'm going to put like the terminations of the input and output, and I'm going to connect them to the transmission line. Very easy and straightforward. Okay, so now everything is set. The parameters are set correctly. The S parameter simulator is right here. Let me actually make these parameters visible here for you. I think I forgot to put the it's right here. Okay, everything is fine. Alright, so now I'm gonna hit this simulate button, and it does the simulation for me. So let's take a look at the S11. If the line is perfectly matched to 50 ohms, then the S11 should be something around I expect minus 40, minus 50 or something. So S11 in dB, let's see, it's 42 dB, which is good. We have to take a look at the S11 on the Smith chart. We can see that here is right in the middle, perfectly matched to 50. The other things that we need to check is the S21, or basically the insertion loss of this transmission line, again in dB, to see how much loss we will have at 2.4 gigahertz. It's giving me almost like 0.11 dB of loss. And also we can take a look at the phase shift of the line to see if it gives us a correct phase shift. So you're going to click on the phase, and at 2.4 gigahertz it's giving me around 90 degrees of phase shift, which is perfect for this simulation. Alright, so I think that is it for this video, and in the next video I'm going to show you how to simulate the same transmission line that we already designed in HFSS, and then we're going to compare the results in HFSS with these results in ADS to see how close we can get to these values if we design the transmission line in HFSS. So I hope you like this video. If you like, please hit the thumbs up button and also subscribe to my channel. Thank you very much.